Welcome, everyone, to today's SNIA CMS community webinar, Accelerating AI with Real-World CXL Platforms. I'm Arthur Sinio, and I'll be guiding today's session. As artificial intelligence workloads continue to scale, memory capacity and bandwidth have become critical limiting factors, taxing even the most advanced GPU infrastructure. Today's webinar will explore how Compute Express Link CXL is redefining the AI and machine learning landscape by unlocking high-capacity, cost-effective memory architectures and delivering scalable infrastructure for next-generation workloads. We are excited to have with us a panel of leading experts. We have Steve Scargill, the Director of Product Management for CXL and AI machine learning at MemVerge, where he leads the development of software-defined memory solutions leveraging CXL technology. We also have Anil Godbole. He is the Senior Marketing Manager at Intel and co-chair of the CXL Marketing Workgroup. He specializes in memory SerDes technologies, including DDR, CXL, PCIe, and Ethernet, and has played a key role in advancing CXL technology within Intel and the broader community. And lastly, we have Andy Mills. He's the Vice President of Advanced Product Development at Smart Modular Technologies, now known as Penguin Solutions, where he leads initiatives on CXL memory products for data centers and AI applications. Together, they will help us understand how advanced memory tiering, KV cache offloading, and distributed inferencing are transforming LLM performance and delivering better efficiency at scale. A few slides about SNIA. SNIA, the Compute Memory and Storage Community, we are a growing collaboration of over 200 corporate members and organizations with more than 2,500 active contributors and 50,000 IT professionals worldwide. This is the hub where we advance cutting-edge technologies and engage the broader ecosystems on transformative infrastructure topics. At SNIA, we focus on engaging users, educating the industry, accelerating standards, and driving technology adoption. We achieve this through public demos, code hackathons, programming memory workshops, and comprehensive educational content like blogs, webinars, and podcasts, all accessible at snia.org. And lastly, we have the SNIA Persistent Memory Special Interest Group, where we advance persistent memory and CXL technologies. We host hands-on programming workshops and hackathons to expand memory innovation across the industry. If your goal is to learn, collaborate, and shape adoption, this is the group to join. And this is our legal notice. I'm going to just skip over that. All right, just one reminder before we start with Steve. So please ask questions. I'm going to be tracking those and getting to those at the end. For whatever questions we may miss, I will have a blog, so we'll track those. Also, please provide your feedback, rate the presentation. I'll remind you about that at the end. And then lastly, the presentation will be available for download during this presentation. So with that, I'm going to kick it off over to Steve.
Yeah, I appreciate it, Arthur. Thanks very much for the warm welcome. So hello, everybody. I'm Steve Scargill. I'm going to talk about how software, particularly on the AI side, is going to take advantage of CXL. So I'm going to talk about some examples that I think are ripe for CXL adoption in AI and making it great for AI and LLM at scale. So I don't think anybody's unaware that AI is insatiably demanding on memory right now, particularly on the capacity and the bandwidth side. So this is where I think CXL is ripe for being a pivotal technology for addressing some of these bottlenecks and capacity challenges that we have. So let me kind of guide you through what I think are some of the focus areas and what I'm looking at the MemVerge side. So we've gone through a few eras over the past few years. We're currently in what we call the context engineering era. We've kind of been here for a while, but now in the past few months, it's actually got a name. And really what this means is that rather than focusing on system prompts and RAG, those are still part of the problem, we're actually looking more broadly. So we've kind of zoomed out a little bit. And we are looking now at, what is the user asking us and what is the user asking the model to do? what has the model been trained on? So that universal knowledge, as we call it. What are the system prompts and instructions that we're telling the model and how it should perform, and results that should be returned back to the user. And then we also include additional information. This is where the context comes in. So what has the user been talking about in the past? It might be a new session. It might be an old session from several weeks or even several months ago that they keep coming back to. Then we get into the kind of the low level stuff. So the short-term knowledge, which we call a KV cache, and this predominantly lives on GPU, but I'll show how this is becoming more of a challenge for GPUs and how we can solve that with traditional main system memory and CXL. And then we get into the long term. So we've known about RAG for quite some time. So that's kind of our corpus and database of enterprise knowledge. But then again, with all the other information that we have available, we've got episodic, procedural, and semantic type of memory that we need to include in our prompts, and what the LLM should be available and using. And then agents. So this includes, the agentic era, all the A2A and MCP that are now dominant in how we design LLM solutions. And then more recently, if you're using ChatGPT or Anthropic or Gemini, they're all kind of remembering what we're talking to them about. So me as a product manager, I like to ask a lot of Jira and Epic type of questions. So those models are now learning that those are the types of responses that I like to get back. And that's what we mean by personalization. So there's a lot of work in this area. And of course, it requires an awful lot of data to be available to these LLMs at high speed, high bandwidth, low latency. So I'm going to focus on one little area of that diagram that I just talked about, and it's the KV cache. So this is kind of the heart of inferencing. And if you're not familiar, the way that LLMs work is that we cache previous tokens as we generate them, so that we don't then have to regenerate them if we're having a really long conversation. So, some of these models now are into the million token context windows, which is ginormous, right? So this is what we're talking about when we're talking about the KV cache and that short-term memory. It's kind of what are we talking to the model right now, or whatever fits into the context window of that model. But like I said before, we're also interested in what's happened before that, right? So this is a sliding window. We don't want the previous interactions to be lost, because that could become useful in the future. However, caching all of this information has a memory tax on that GPU. There's only so much high bandwidth memory capacity that these GPUs have. So we need to kind of find ways of dealing with this. And there are many ways that we can do that. But before I get to that, I just want to explain a little bit more about why KV cache is so important and why it's dominant. I won't go through the math here, but this is kind of how you would calculate for your particular scenario based on the model and models that you want to serve, how much GPU memory you require. So we take in the model weights, and that is wholly dependent on the model that you've chosen. So how many parameters it has. The activations and the overhead are typically fixed values based off of the framework that you're using. Another thing that's variable is the KV cache, right? Again, it depends on how much interaction this particular model or session has had with the user or users. So let's talk a little bit more about that. So in this example, top left is the scenario that I use. So 7 billion parameter model, precision of floating point 16, context window of input-output tokens of about 8,000. And then the internal mechanisms of that model are 32 layers and 4,000 hidden. So if we just do the math based on the slide before then I get a number of around 21 gigabytes. And that's before a user's even kind of pressed any keys on the keyboard to interact with this model. So I plotted this on the right-hand side. That's what that chart's doing. It's a stacked chart. So I take in all of the variables, and then the shaded purple area is the KV cache, and that single green line across the top there is the total sum of all of my model weights, my activations, my overhead, etc. So the green dotted line is 80 gigabytes. So that's the size of high bandwidth memory on a single H100. And I highlighted that if we exceed that, then you're going to get an out of memory condition. So if I wanted to serve 100 users, you can clearly see that I'm not going to be able to do that on a single GPU. In fact, the math on the left shows that I can probably support up to about 16 users on a single H100. So if I wanted to do 100 users, I'd need at least 6 or 7 GPUs. But what the takeaway here is that the KV cache dominates the memory requirements of those GPUs. So very quickly, if you're not using the high-end GPUs, then we need to find ways of offloading and managing this memory without it being lost and having to be recomputed. So there are many ways that we can do this. I just kind of highlighted 4 here. One of which is the expensive option. We just go buy more GPUs to gain access to more high bandwidth memory, and that's down to the individual use cases. But the cons is obviously that is an expensive approach, and we're just buying GPUs at that point, mostly for the high bandwidth memory. If you actually take a look at the utilization of the compute side, simultaneous multiprocessing, you'll find they're very underutilized. Most people are struggling to get them more than 20 to 30% utilized on a big cluster. So, but we can shave a bit of memory off the model parameters by quantizing. So we can use smaller models, but the downside of that is that we will lose accuracy and the results may not be really what you want. So there's a trade-off here of size and accuracy versus available hardware capacity. We can scale out the solution. So we can definitely run multiple servers. Each server's got multiple GPUs in it. We can have routers that will intelligently route user sessions to the correct server so that we're reducing the overhead of trying to recompute KV cache. If user A had to start it off on server 1 and then was bounced over to server 2, they would have lost all of that context that they've generated on server 1, and we'd have to recompute all of that. So that's not ideal. The fourth option on the list here, and one I'll talk a bit more about for the context of CXL, is actually offloading that memory back off to CXL and DRAM, so off to the main CPU. And this is very similar to how we do memory tiering in Linux today with the storage memory hierarchy pyramid. So as we drill down a bit more here, the diagram left is kind of what we can do today. So a system with just DRAM only. We can reserve or pin memory in main system memory, and that has the advantage then of the GPU can do DMA operations. So if it needs to offload data, it does so in a very efficient manner. However, you are pinning and reserving that memory, so that capacity that you reserved has to be done up front, and you can't then use that memory for anything else while the application is running. So the proposal here, at least for CXL, is that we can have dedicated devices targeted for just hosting KV cache. So that's the one in the middle here. So then I'm able to fully utilize the memory capacity or the DRAM capacity for my applications, or indeed I could reduce the BOM cost and reduce the amount of main system memory that I need for my system. And then Anil's going to talk a little bit more about this, so I'll just briefly touch on it. But we can use the combined bandwidth of both DRAM and CXL so that we're not losing out on the performance when transferring data between main system memory and the GPUs. So this, I believe, is a perfect fit for this warm tier of data when we have to offload between the GPU and host. So again, the benefits of this approach is that we are freeing up that high bandwidth memory. So the TCO of the whole solution could be reduced if we don't need to go and buy as many servers or as many GPUs to service the number of users that we have. So that also helps with data center capacity. We don't need as many racks, we don't need power, cooling, etc. So overall, I think the benefits are substantial. And of course, as model gets bigger and bigger and the context window continues to increase and the number of agents we have increases, then we can service all of those in an efficient manner. So I talked mostly on kind of a system level approach, but I also wanted to kind of describe what we're doing at scale. So when we're scaling up and doing hundreds or thousands of users. So the problem with scale, as you may have seen from the previous slides, is that I can go off and buy lots of servers and I can put lots of GPUs in those servers, but again, those GPUs, the compute side of them is very underutilized, right? So I'm literally just buying GPUs for memory, which is an expensive way of doing things. So, and like I said before, right, if those users are not routed to the correct server each time, we have to go off and recompute all of that stuff. So that's very wasted cycles. The bandwidth as well on the memory side. Again, at scale, the demand of memory increases quickly, very much overwhelming the GPU capacity that I have. And then today we have the ability to move data between servers relatively efficiently over RDMA, TCP if you need be. But I think the fabric capabilities of CXL will definitely give us a much more efficient way of moving data between systems. And Andy's got a great slide on what the future of CXL is in this area, and that's very exciting to me. So there are many leading platforms in this area. You may have heard of them. You may be using them, right? So NVIDIA has Dynamo. That's relatively new. LLMD is the newest of this list. This is the IBM Red Hat solution. VLLM, Mooncake, and there are many more. And the principle here is that we're just disaggregating LLM inferencing from the infrastructure. So the challenge, of course, though, is that we have to manage memory at scale. So we have to manage not only local memory on each node, but across the entire cluster as well. So the way that these platforms do it is that they use the memory storage hierarchy pyramid. And today they're only capable of tiering between the GPU, the main system memory or CPU, and storage. And that might be local NVMe. It might also include some shared storage or object storage. But the goal is to try and enhance the time to first token. And then once you've got that through to the user, then how many tokens per second can you generate? So, and again, I believe the CXL fabrics can definitely facilitate this high throughput, low latency requirement of inter-node communication or inter-LLM communication, so that we're generating even higher optimization number of tokens per second for the users. So I'm going to talk about 4 different platforms, the ones I've mentioned. I won't go into any details here just because we're short on time. But I do want to point out where in the stack CXL should fit, and certainly at Memverge where we're looking at optimizing these solutions. So starting off with Dynamo and Nixel. Nixel is the low-level inference transfer engine at the bottom of the diagram here. This is a pluggable architecture. So it looks very similar to a lot of the other solutions that I'll talk about, but it's also very easy for us to create a CXL plugin. And that plugin could be just using local CXL. And in the future, we have designs for using shared memory across multiple different hosts in the fabric. And you can see in the bottom right-hand corner there, the KB Cache Manager. This is the thing that's responsible for migrating data up and down the stack between all of the available tiers of memory and storage that this particular environment has access to. So that's something that we're working on right now. Mooncake is very similar. In fact, Mooncake is also supported by Nixel and Dynamo. So the proposal here is that we would replace the RDMA in their architecture diagram with CXL sharing and pooling. LLMD again is very similar. You can see here that they actually use Nixel is one of the options for configuring this platform. So again, if we modify Nixel, then LLMD could use that Nixel plugins that we've modified and use the CXL fabric here as well. Note also that the prefix caching in the bottom here, the LLM cache, is another way of caching data in LLM at scale. So again, that's really ripe for memory expansion and bandwidth. And then finally on my list is VLLM. Again, just kind of showing you that they have a pluggable, shareable KV cache storage, again, based off of today's technology. But again, if we replace this or augment it with CXL fabrics, I think we should get some significant improvements in overall performance. So just the takeaway from my section here is that we're definitely in the era of context engineering, right? All of the things I talked about. It's not just focusing on prompt engineering anymore, or specifically focusing on RAG or one particular area, though they are very important. And that, secondly, the KV cache dominates the GPU requirements, particularly at scale. So we need that ability to offload that KV cache and or model parameters if they're not being used, freeing up that precious resource so that the GPUs can do what they do best. And by modifying existing frameworks, like I described, using CXL expansion and sharing, I think we have a very bright future for CXL in the AI era. So I think with that, I'm going to hand over to Anil, who's going to talk more. So thank you very much.
Anil, you're on mute.
Oh, yeah. We're used to all talking on mute.
All
Okay,
right.
hello everyone. I will go next now. But before I begin, I want to thank Steve for a great introduction on the mechanisms and the needs of modern AI infrastructure and how CXL memory and fabrics can really help going ahead. And in my talk, I will talk about one other mechanism of AI workloads where CXL memory can be of big help. Yeah, and before I begin though, I want to point out the fundamental reason why ever more memory is being needed per CPU socket. Today's data center workloads have very high memory footprints and therefore need high compute power. CPU manufacturers have responded by offering CPUs with ever high core counts, and as these multiple cores simultaneously crunch the workload, it puts a big demand not only on the memory capacity, but also the bandwidth. Today's AI/ML workloads demand more of the latter, especially when it comes to subsequent token generation in a generative AI session. Let us see how CXL can help here. A quick primer on the value prop of CXL attached memory. Most of you probably already all know this, but the first intuitive value prop of using CXL memory is to simply increase the memory capacity of the system. Reduction in SSD accesses due to DRAM misses is a big benefit here, right? Improving the CPI, cycles per instruction, or the processing time of a workload. The workload will finish much faster. The second box shows how CXL memory can be used to increase the total memory bandwidth. And the last one, but not the least, shows how CXL memory can be used to reduce the overall memory TCO. I will touch upon that briefly in my next slide. But today we will focus on the second box. We will first explore how bandwidth is expanded using a technique called address interleaving. And later we will see how we can put this bandwidth for good AI use. The primary way CXL attached memory helps with TCO savings is by not having to use higher premium DIMMs. I mean, in terms of dollars per gigabyte. When you are trying to build a certain memory capacity, and I'm showing some examples there. With CXL, we effectively have more memory channels on the CPU beyond the local DRAM. And therefore, one can realize the total required capacity simply by redistributing the needed DIMMs over many channels. And so this will allow you to use lower price DIMMs. Take a moment to look at some of those capacities, like 1 terabyte, 2 terabyte, rather than having to resort to 128 and 256 gigabyte DIMMs. You can make use of the best bang for the buck DIMM size today is the 64 gigabyte, and how you can build that capacity. And if the memory controller, and another benefit, if the memory controller on a CXL module supports DDR4 memory, then the savings can be even more. Not only because the DDR4 DIMMs cost less than the equivalent DDR5, but also one could simply reuse the old DIMMs, which they are about to recycle due to the ushering of the DDR5 era. If you can reuse those, then the price of CXL memory is basically free, other than the controller cost. And then having more channels to access with CXL, the total memory bandwidth of the socket also increases. In fact, we will be leveraging this technique in my talk. Now back to our feature presentation. This slide shows how address interleaving is used to increase bandwidth. The method is similar to how bandwidth of storage drives have been enhanced using RAID techniques. The concept is the same, but applied to data stored in the memory. Rather than keep all the data for a given workload contiguously in a single DRAM channel, like how a normal OS will allocate the memory space to a workload, you stripe it across all channels. So when a workload accesses this data, all the memory channels will contribute their portion simultaneously. In this graphic showing Intel's GNR AP CPU, now called the Xeon 6900 series, which supports 12 memory channels, and one can add another 8 by using the 4 by 16 CXL links, we can realize a bandwidth speedup of 20x. The OS does this by striping the virtual pages across memory channels, physical addresses. The graphic is showing only 2 nodes, one for the main memory and one for all the CXL channels. But in practice, one can extend that to multiple NUMA nodes when the DRAM channels are further split into sub-NUMA clusters. The capability to set up this data is now available in Linux, in an interlude way, with the kernel version beginning 6.9. I want to acknowledge members along with other contributors, Micron and Hynix, for contributing this capability to the Linux community. And one can adjust the allocation ratio. This scheme is quite flexible. One can adjust the allocation ratio of how much data you're going to keep in main memory versus the CXL node. That ratio, which I show in the slide as M:n, M being in the amount of data in the main memory versus N in the CXL side. That ratio is based on the bandwidth ratio between the 2 nodes. So note that the bandwidth of a DRAM and CXL nodes is not constant. It varies depending on the read-write access pattern of the workload. For example, for read or write intensive workloads, a DRAM channel's bandwidth exceeds that of a CXL's. But for mixed read-write pattern workloads, CXL is higher since CXL has bidirectional channels. AI inferencing workloads are typically read-intensive, favoring higher weight of the value of M to the DRAM memory. And to reiterate the TCO play here, rather than use, say, all 128 gigabyte DIMMs on the CPU memory channels to meet the workload memory footprint, one can spread the memory between main DRAM and CXL side using the less expensive DIMMs. And this not only gives lower cost, but also increases our bandwidth, which is what we are going for. Now, one might wonder why the higher latency CXL memory does not come in the way when you interleave them with a faster memory like DDR5. This slide explains why the net memory access latency is actually reduced when you do this address interleaving scheme or configuration. As the blue graph shows, which is the DRAM-only curve, when multiple cores on a CPU start doing memory accesses, the memory controller becomes a bottleneck. The memory controller for a given DRAM channel becomes a bottleneck and starts queuing up the transactions. This shoots up the latency for the requesting cores, but not because the DRAM is getting slower. It's the queuing up effect inside the memory controller. But with CXL memory, you have now added channels. Now the memory requests can get steered across or distributed across many more memory controllers, thereby flattening the latency curves as we show in the orange. Right? So basically, as you try to push more bandwidth, using CXL memory will offer you, still reduce latency. And at some point, of course, it saturates to the far right. But in the picture shows about 250 gigabytes of extra bandwidth can be had without big latency increase. And a little side note here, using this address interlink technique, I have co-authored a paper with the Micron folks to show how many bandwidth-hungry workloads like those in the HPC domain, and along with AI, of course, today's talk is about AI, got benefited. One of the AI workload was actually to execute a small LLM directly on the CPU without using a GPU. So I urge you all to check out the full paper at the link shown here. We'll now take a look at how CXL-based memory interleaving can be a big help in this other AI workloads, which are the RAG-based workloads. As Steve mentioned, touched upon that briefly as part of the the long-term memory and how RAG can be used. So first, a little primer on RAG, or the retrieval augmented generation. It is expected that this technique will be the biggest growth area for AI inference in the future. This is mainly because of its applicability in analyzing private enterprise data. All the LLMs out there in the public domain today have been trained using only openly available data on the web. Hence, such an LLM will not be able to answer or analyze data private to an enterprise. RAG is a method to allow a public domain LLM to analyze private data. The graphic here gives a quick overview of how this is done. The lower part of the graphic shows how data is first stored or embedded using some special techniques in what we call a vectorized data format. This format is quite different than the normal text or binary format of document stores. Although the source data is the same, meaning you can take the same data, store it as a document, or you can store it as vectorized after doing the vectorization. The vectorized format lends itself to semantic parsing of data, which a simple doc store will not be able to do, right? So meaning of double meaning of words like kite or other English words, right? So the exact mechanism of embedding data is beyond the scope of today's talk. I would suggest reading a seminal paper called Word2Vec, which is available in public domain. The embedded data is kept as a vector database shown in the graphic above. It shows that it's all stored on CXL, but there's a little error here. For my talk, I'm going to talk about how it can actually be interleaved between the main memory and the CXL memory to improve the bandwidth. In reality, the vector database, as I said, is kept as interleaved between the two sides. And depending on the enterprise, such databases can be in terabytes and will not fit in the main memory alone. So if CXL wasn't available, then the leftover would have to be kept on SSDs, slowing down the accesses. But once the vector database is ready, then the queries can begin. This is shown on the top part of the graphic. When a query comes in, a set of data relevant to the query, called context, is extracted from the vector database. This lookup is typically done using a CPU. The retrieved context is then fed to an LLM, which can be running on a GPU attached to the CPU, which can then issue an answer or response to the query. So using this technique on this slide, I'm showing some speed up examples of a RAG database lookups done with the CPU with integrated memory configuration, interleaved memory configuration. The speed up performance numbers reflect the speed up over doing the same search, but with DRAM memory alone. There are a few different vector databases which I'm showing, but I'm sure most of them, pretty much all of them, should benefit with the added bandwidth of CXL. I'm showing the results for the three more popular ones, which are, and mainly because they are now available in public domain. All these were run on the Intel Xeon CPUs with various CXL ecosystem partner devices. And I give the credits to everyone on the slide. I can provide more details on the detailed configurations if there is interest and in the backup slides. But it is pretty impressive how we are getting, easily around 25% of speed up increase. So just want to show a slide that that Intel remains fully committed to support all CXL Intel CPUs to support the CXL protocol evolution going ahead. With the recent launch of Xeon 6500 series processors and 6900 before that, the latter being for the enterprises, we have now completed the launch of our 6th generation family, previously codenamed Granite Rapids. It offers broad support for CXL in the sense that all CPU SKUs in the family offer CXL support. And we have some enhanced CXL modes on the CPU. One other mode I didn't talk about here, called Intel Flat Memory mode, is quite, it's proving quite effective for document databases. We got a recent endorsement from SAP commending that mode. I urge readers to look at on the web, and I'll also provide a link in the backup slides. So that pretty much brings up to the end of my talk. So to summarize, right? So CPU will certainly play a big role in the AI revolution in the coming years. The many workloads like RAG, small LLM inferencing, where CPUs can do a job more economically without needing a GPU, and sometimes depending on the LLM size. And CXL memory will, of course, play a big role for scaling these workloads. And the Intel Xeon 6900, 67, 6500 CPUs, all coupled with CXL ecosystem on both hardware and devices. Now today we are close to 60 devices available. They are on the integrators list on the CXL consortium website. So the ecosystem is pretty mature, and it's all available for you to run your AI workloads with the CPU. So that is the end of my talk. Thanks everyone for your attention. Pass on to the next speaker.
Hey guys, this is Andy Mills. Thanks, Anil. Thanks, Steve. That was great. Great system level overview, software, hardware, and architecture. I think I got the slightly easier job of trying to present here, what hardware we have available to do all this and run all this stuff on. We've come out of I think this is the transition year for CXL. It really is. I think the evidence is really showing now. You can start to buy CXL now. Up until late last year, we were demonstrating, doing a lot of proof of concept. So this is a great transition year, I think. So let's talk about the hardware a little bit. I'm re-summarizing a lot of what Steve and Anil have already really touched on, but today, if you look at what the issues have been around AI, we've seen from Steve's talk especially that the scaling out memory or scaling up memory has a tax, and there's capacity limits you have to overcome. So the number of RDIMMs, for example, that you can physically attach to a CPU, that's one capacity limit. For a GPU, you're limited by the HBM directly attached to the GPU before you have to start using RDMA and DMA to get outside that domain, or scaling up the number of GPUs, which incurs, networking overheads. And so you can see there's kind of a compounding problem as you start to scale. The more GPUs, the more CPUs, the more networking hardware starts to push up the amount of power, that is needed. And we all are hearing, the gigawatt data center stories now of how, those are being deployed or planning on being deployed. Power is becoming incredibly important aspect of what we're doing as well, beyond just all the scaling and stuff that Neil's talked about with with scaling up the bandwidth. So the industry does need to solve for this higher performance, higher capacity memory for CPU and GPU, and you've got to minimize power at the same time and minimize heat generation. So not a trivial task. So let's talk about what's available, what's out there today. If you didn't have CXL, let's start there first. As Anil's pointed out, the cost, the TCO, is important in CXL simply because as you start to scale up memory, you hit that RDIMM limit, which, as you can see shown here, is the blue kind of black interleaved slots there in the middle of the server picture. You're talking about having to go from 64 gigabyte to 128 gigabyte RDIMMs up to 256. You can see it's not a linear scaling. The problem, as we all know, is that the cost of 256 is just because it's using 3DS, 3D stacked memory, TSV technology. It's just harder to make. It costs more. Whereas with 64 and now 128, you've now got monolithic die DRAMs. It's much easier to manufacture, and the costs are going to be to be lower. So we do expect that 6x, for example, for 128 gigabyte to start coming down as more and more of that deploys in the industry. But you can see how that translates, on the bottom table. For a typical off-the-shelf AMD Turing system, 12 per CPU, 1 DPC mode is a typical configuration you see out there. And I'm going to just give examples. I know there are maximums you can go beyond that, but I'm going to give typical configurations you can buy off the shelf today. You're talking maxing out with 256 gig RDIMMs at around 6 terabytes. The same for Intel SP system, taking the best case for Intel, that's about 8 terabytes. So that gives you an idea of what the physical limits are today of off the shelf without CXL. So industry's got around that in the past by using a number of techniques. Obviously, scaling up, scaling out is one. The other, inside the box, if we just focus inside the box for a second, the other way to do this has been to increase the number of CPUs. Typically, we've been in plenty of meetings where they said, well, just increase the number of CPUs, either go from a 2-socket to a 4-socket, and double your memory, and use NUMA to access that memory, as we show here in the top left. That's how we've been solving the problem today, and to a large degree. But that gets expensive, and I think given the scale that we're talking about here, the cost of implementing 4-socket servers is substantially higher than 2, of course. So there's going to be, a lot of focus on trying to keep things in the kind of the 2-socket kind of mode here. Now we got the other aspect which has been very popular, is using SSDs. And we talked about SSDs as either a page overflow, a cache hit or miss by the kernel, for example, can result in paging memory out or in and out of SSDs. Once you do that, you've got a huge performance hit intact. So if it's about bandwidth, as Anil showed earlier, once you hit that SSD tier, you're talking about dramatic slowdowns. And in an age where we're trying to make AI more real time than we are, just trying to solve the problem and waiting a few more days for something to complete, that's no longer sufficient. You've got to do this in real time. That demands higher levels of memory directly accessible to the CPU and eventually the GPU as well. So let's look at what CXL offerings are out there. There's 2 basic configurations you see, and I've just chosen one particular vendor here just as an example of what you see on the web. And now you see most of the tier 2, and I'll show you in a second example of a tier 1 server vendor now that you can go out and buy to get CXL up and running in your lab. So let's look at the first one on the left, is actually using a GPU class server. It's by far the easiest and simplest way to add CXL to your kind of data center rack today, or standalone server, is just to buy something with far more PCIe lanes and slots that are CXL capable. Now, it turns out there's a couple of those now coming out. They're available now. We're using the example in the top left of a Penguin-based server, for example, where we've got 8 PCIe by 16 slots where you can add 8 of the smart modular add-in cards that have 8 DIMMs on them. So that's 8 times 8, 64. You get an extra 64 CXL RDIMMs now you can add to the already 24 if you're AMD, or 32 RDIMMs if you're an Intel Granite Rapids SP system, for example. So if you do the math, now you look at the table on the bottom left here, you're talking about scaling AMD up to now 22 terabytes. And in fact, that's one of the options that I think Penguin's starting to offer. And then on the Intel side, we'll be looking to do something similar very shortly as well, where you're getting up to as far as 24 terabytes, or using the 12 channel, maybe the AP processor, maybe slightly less than that, but you're now talking into the 20s of terabytes rather than being capped at that 6 or 8 terabyte limit. So you got a 2 to 3x gain just by going CXL. Of course, you're going to have to trade that up. A lot of system variables involved here. You got to trade those sockets up against GPUs. So what we actually envisage for RAG, for example, is you might not use all of those slots for the CXL. You're going to use some for CXL and some for GPUs. So remember that it gives you that extra flexibility, but you do have that trade-off you have to make. Now, on the right-hand side, you're talking about E3. This is where I think CXL started out for us. It's kind of a removable option, convenient plug-and-play kind of story for E3 servers. E3 servers, unfortunately, kind of lag behind from a CXL perspective. We're just seeing the first CXL E3S servers come out now, and here's an example of one we see. But first and foremost, you're limited. You're limited by the number of slots. But the good news is they're now here. So you can trade off. Obviously, some of those slots are going to be used For NVMe storage, for example, you still need NVMe in your life, of course, and to store for persistency purposes. But I think the emergence of E3, I think you're going to see a lot more of these systems come online throughout 2025, starting with a few already available. So typically 4 or 8 bays are now being reserved for CXL in a typical E3S server. And obviously, check with your favorite server vendor to see when that option is available or if it's already available. And again, the only limitations today, because of that 8-slot or 4-slot limit, of course, is that you can't put as many CXL adapters in, but you're dealing with a shorter, more classic server architecture where you don't need that overhead of having to support the GPU chassis or the GPU bays, as it were, as you see on the left-hand side. Again, you get to about 10 terabytes. You're adding a little bit beyond, but as Anil said earlier, and I think the Micron example that he showed there was actually using CXL E3 devices just like this, because you're getting the benefit of spreading that bandwidth across CXL when you start interleaving. So that's kind of what it looks like here. Now, one of the significant steps in about a couple of months ago, we had the first tier 1 OEM starting to offer CXL and ready-made, when I say ready-made, something that has been proven out. You can buy it off the shelf with CXL already pre-tested, approved, and validated. Then the main server vendors themselves are now starting to adopt, which is great news. This is a 4-DIMM add-in card, for example, where you can add the additional DIMMs into the add-in card. And in this case, you're now talking about 2U servers, 1U servers, with a much slimmer, thinner card. This particular card here, the Smart Modular 1-width card, is able to go horizontally, and you're able to kind of stack maybe 4 of these in a system. So not as much as you saw in the GPU server, but certainly sufficient to add another half a terabyte, maybe 2 terabytes of memory to your system. So that's starting to happen, which is great news. So we're definitely moving to the deployment phase again of CXL now. So let's talk a little bit about pooling, because I think CXL has definitely been the focus. I just talked about here is direct attach or local CXL that's sitting inside the box. By far the easiest way to add it, if your service supports it, is to add that add-in card. No cables, nothing else involved. But there is a case where you now want to take that memory out and physically disaggregate it. And I'm not going to go into detail on this, but there are kind of 3 tiers that we're starting to see. This is something we put together internally at Smart and Penguin to try and show, well, okay, there's 3 classes of memory pooling we expect to see evolve. We've been talking, and the industry's been talking a lot about the middle slice there, the CXL fabric memory, where you're physically cabling CXL PCIe outside the box to your memory pooling box. We'll show you an example of that in a second. But there are these other markets. For those of us who come out of the storage world, for example, the storage area networking world, there was always kind of 3 tiers, right, of solution. And we expect the same thing to kind of evolve here. You've got your very high-end ultra fabric, UA link and stuff like that is always going to be there. You've got NV link, you've got something I'll show you in a second that we're working on is Smart. That's our own version of a ultra fabric, silicon photonics-based network. CXL memory, which is kind of the mainstream of where things are going to happen initially for pooling. And then you've got Ethernet fabric memory. We shouldn't forget about that, because Ethernet has been that great stable networking, approach that most people are familiar with. You don't have to learn switches, or you don't have to learn what Ethernet is. It's a very well-known data center infrastructure component that people know how to use. CXL is a little newer, right? Every time you deploy anything new, it takes new expertise and new procedures. So we do expect there to be an Ethernet fabric, version of this that leverages CXL. Maybe it might not be CXL over Ethernet per se. It might still be traditional RDMA, but we're now seeing early signs and working with some partners taking that same CXL add-in card, for example, and putting it behind an Ethernet to CXL fabric switch. So a lot of stuff going on in that area, which is pretty exciting. So the first one I think here that's now coming online, and I think the focus here is to talk about stuff that's available in the next 90 days or so. This is one that just got announced from Liquid. And I think this is a great example of a first generation CXL disaggregated solution. actually leverages the same component we use in servers. Our add-in card, for example, here is the typical PCIe add-in, but it's now sitting behind an active switch inside that box. So you can, for example, support 10 of these cards, with 8 of them. That's that's up to a terabyte of using 128 gigabyte memory that you can now share. 10 terabytes, sorry, you can share amongst multiple servers up to, I think it's 5 in this particular case. And then you can expand beyond that with additional CXL switching. So CXL, CXL doesn't need CXL3, just to be clear, to do this. This is CXL2 with a very fundamental, basic way of being able to disaggregate memory. So that's really exciting news from our perspective. This is really, from our perspective, exciting development. So you've got both in the box and you've got shareable memory now when you want to start building out, racks or clusters of servers, all sharing the same RAG vector database, for example, so you're not moving stuff around anymore. Finally, I just want to touch on a little bit of, I think exciting stuff that's going on right now. And this is active. This is not science. I mean, we've heard of silicon photonics been used in the telecom industry a lot over the years, and for general optics, for I/O. But there's a huge move, as we saw recently from NVIDIA with the GTC, was the talk about using silicon photonics for the switching. We're solving a problem here that basically is related to both power and bandwidth. How do you scale beyond what we have today? So the holy grail here, in a way, is how do you get HBM class memory disaggregated? We've all talked about DDR5 and being able to do that with CXL, which is perfectly adequate, but you need to go a little bit beyond for things like, a lot beyond for things like HBM, for example. HBM physically, as we see on the left here, has like 1,000 physical signals you have to route between the GPU and the HBM3, 1,000 plus physical lines and signals. So there is a development going on right now. I'm excited to say we're involved with that development, that using silicon photonics, replacing that HBM memory, not replacing it, putting an I/O device there essentially in its place, or even potentially integrated into the XPU itself, and then coming straight silicon photonics out the top. As we can see the little tiny diagram there, you're coming directly out of the top of the silicon itself, optical, using optical fiber. You do the conversion in that silicon photonics layer, but you're basically going literally fiber to fiber all the way through the system to the the host in this particular case before it gets converted back to electric again. So you're removing all those stages of converting between optical and electrical. So that's a very active program. We're trying to shoot for our first demonstrations next year. So this is a very, very exciting development, and this is kind of brings us to the final slide, which is kind of a peek at the future. What does the future look like? One of the challenges that we face beyond sharing memory between CPUs is how do you share memory between GPUs? And of course, Steve showed earlier the scale up model where you're scaling out by adding more GPUs, but ideally you'd really like to get the GPU more memory that it can directly access, not through RDMA, more as directly addressable memory. And again, the second ask would be, can I do that at HBM rates, or as close as I can get to it? So this is kind of what the future looks like here. The optical and silicon photonics enables you now, for the first time, to access off the GPU or off even a CPU that's trying to access HBM memory over silicon, photonics to fiber link, and then back into a optical memory module that now sits in a disaggregated device. So what you now get is a box that looks something like this: 32 terabytes, up to 32 terabytes of shareable DDR5 in the same box, because now you can do some clever things, caching of HBM and DDR5. CXL, you can run CXL protocols into and out of it. So for example, the top layer there shows the CPUs getting access to the same memory, using CXL protocols, and then the guys at the bottom using native HBM protocols or UA link or something like that going forward. And you're now able to essentially stop moving memory around. You're all working on the same data set. And remember with AI, as we showed earlier, and Neil showed this too, that you're just getting these explosion in the amount of data and the amount of memory. So the less you can move those chunks around, just for the sake of moving them, so that a disaggregated or a distributed network can get access to it. If you can collapse that down to a single, scale up GPU getting access to a larger amount of memory, you can potentially reduce the number of physical GPUs that you need to get a particular problem done and scale it up, more so. It's not that we're talking about reducing GPUs, we're talking about increasing or allowing them to increase in a much more effective and controlled way. Anyway, I'll leave that with you guys, and I hope you enjoyed this chat and intro to AI software architecture and some practical products. And with that, I'll hand over back to Arthur.
Thanks, Andy. Thanks, Anil, and thanks, Steve, for the great content and presentation material. We took a little bit extra time. We have till the top of the hour. We can go with a couple different questions here. I don't think we're going to get to all of them, but certainly we'll post them on the blog. So first of all, there was a question about power consumption. I think Andy there was a couple mentions about power, but was there any analysis done on total power consumption of DRAM, VRAM setup versus CXL interleave setup? Anyone want to tackle that?
No specific measurements at this point. We're actually going into the phase of doing that, and Anil may have some comment on this as well. But from our perspective, I think the goal of disaggregating memory is not to say, look, cool, we just moved it outside the CPU. It's more that we're able to more efficiently control the amount of memory that we can distribute across those CPUs. So we're not over provisioning anymore. So to answer your question, no specific measurements yet. That's something that we will be publishing and working on from our perspective. But you do get, in theory, a net reduction in the amount of power because you're using less memory, and memory does take a substantial amount of power. Now, obviously, you've got to offset that against networking and adding a new appliance and all those kind of things. So absolutely a very good question. And I think, that's probably, now we're going into the practical phase of CXL. That's a good question to get answered.
Anil, did you have any comment about that?
So that's a good question. Yes, you always have to worry about the TDP budget of the CPU. Once the system gets hard, then the CPU will come down in frequency, right? So yes, but when we ran, right, so we were assuming about 25 watts per CXL module, so we didn't blow the power budget that much. We were able to operate the CPU at the rated speed, and so we basically kept the TDP budget of the CPU and didn't blow that. So
okay. See if I get this question right. Can GPU memory have hierarchies similar to HBM, localized CXL type memory, local NVMe, networked NVMe? Not sure if I'm getting that question right, but
yeah, I can cover that one because
Steve,
in my talk, the NIXL piece. This is why I'm very interested in NIXL and the architectures frameworks that I highlighted, because they kind of do this, right? The block manager, the key value block manager in NIXL is entirely dedicated to this particular thing. So at Memverge, we're looking at introducing CXL into that memory storage hierarchy pyramid, so that Dynamo and NIXL have the ability to read and write to CXL as a new tier of memory. And then the other thing that Anil highlighted, right, weighted interleaving in Linux, being able to combine the capacity and bandwidth of DRAM plus CXL gives us that ability as well to use CXL in our LLM solutions. So yeah, stay tuned, I would say, for this one, but entirely doable. Yes.
Great. So we're not going to get to all the questions. I'm sorry, everybody, but we will have a blog and answer those and post those. The presentation will be posted on the SNIA library, accessible there. So again, thank you, Steve. Thank you, Anil. Thank you, Andy. Great content. Thanks for taking time to put this together for the industry to share with them. So thanks again. A couple other items here before we end for today. So we have the Future of Memory Storage event coming up. Anil's hosting a CXL track, so please visit that. We have the SNIA Developers Conference. We have SC25 in November. A lot of access to content on the SNIA website, education listed here, as well as numerous links. So we appreciate everybody's time and attendance, and thank you for participating, and we appreciate all your support. So thank you, everyone, and thanks, guys.
Thank you.
bye, everyone.